Imagine you're on final approach. The weather is poor, and the runway you're aiming for may be covered in water, ice, snow, or slush. How do you land safely under such conditions? In this video, we will explore the challenges and techniques for landing on contaminated runways. Where friction is limited, control is delicate, and every decision matters. You may ask, what is a contaminated runway? We know that standard aircraft landing performance is planned for a dry runway. However, a runway is considered contaminated when its surface has enough water, ice, snow, or slush to reduce friction and braking efficiency. When contamination is present, performance margins shrink, crosswind limits are often reduced, and the risk of runway excursions increases. The key to a safe landing on a contaminated surface is a stabilized final approach and a firm but not harsh touchdown within the prescribed touchdown zone. If the approach is unstable or touchdown is delayed, a go-around or rejected landing is the correct decision. There should be no indecision. When touching down, the vertical rate should break through the layer of contamination so that the wheels can start rotating. A target descent rate is on the order of 2 to 3 feet per second or 120 to 180 feet per minute. Once main gears touch, full spoiler deployment and reverse thrust should be applied quickly to increase wheel loading and allow braking to become effective. Once braking begins, deceleration depends on how fast the wheels spin up and the efficiency of the brakes on a low-friction surface. On a contaminated runway, lack of sufficient wheel speed is often the limiting factor, not brake failure. One caution is that emergency or memory drill modes, like selecting emergency braking, can disable the anti-skid system. On a wet or contaminated surface, that raises the risk of wheel lockup or aquaplaning. Reverse thrust contributes roughly 20% of total braking on slippery surfaces. However, certification of aircraft braking performance is based on dry runway assumptions. So contaminated runway operations rely on advisory friction data and may require additional caution. Maintaining directional control is one of the trickiest parts of contaminated runway landings. The control column or side stick should be centralized immediately after touchdown to avoid asymmetric loading of the wheels. Initially, rudder is usually effective up to about 80 knots, and sometimes less. But if control issues arise, reverse thrust or differential braking may need to be reduced or canceled until control is regained. If auto brake selection is producing differential brake release that worsens yawing, switching to manual braking is often recommended, sometimes by completely releasing the brake pedal on one side. As speed decreases and rudder authority fades, the effects of even small asymmetries become more pronounced. Reverse thrust asymmetry, differential braking, and reduced nose gear adhesion all worsen directional stability on a contaminated surface. Autoland systems were developed primarily for low-visibility landings, not for low-friction runway surfaces. While Autoland may provide a reasonable touchdown, its derotation and rollout logic are not optimized for asymmetric braking or varying surface friction. Many aircraft procedures recommend reverting to manual control after nose gear contact, especially when directional control becomes uncertain. Also, when using Autoland in potentially contaminated conditions, obtaining full approach protection from ATC may help mitigate ILS disturbances and improve safety. One major challenge is uncertainty about the actual runway condition at the time of touchdown. Delays in inspections, delays in ATC updates, and limitations in friction measuring devices all contribute to risk. Friction measuring devices can give varying values depending on contamination type, and none are reliable in all conditions. Since the adoption of the global reporting format, friction values are no longer reported, only runway condition codes. Pilots must carefully interpret meta-runway state groups, SNOTAMs, RCC, and any unofficial pilot or ATC observations. Even when a runway is reported as uncontaminated, partial contamination or unexpected liquid water may still be present on touchdown. Always plan for the possibility of reduced friction and maintain margins. Let's look at a few real incidents that highlight the dangers. In 2020, a Boeing 737 overran a wet snow-contaminated runway in Halifax by nearly 100 meters. The crew had assumed friction would be adequate, but had not loaded new performance data for the shorter runway. In 2019, a Boeing 767 landed on an icy runway, lost directional control as speed dropped, and rotated 180 degrees before coming to rest facing the runway threshold. In another incident in 2003, an Embraer 135 overran a slush-covered runway in Norwich after a late touchdown in slush. There were no injuries, but this incident underscores how even light contamination can lead to excursions. To summarize, we can say that 1. Always plan for contaminated runway operations rather than assuming dry conditions. 2. Use a stabilized approach and firm touchdown. 3. Deploy spoilers, reverse thrust, and brakes promptly and wisely. 4. Monitor directional control carefully. Cancel reverse thrust or switch to manual braking if needed. 5. Don't hesitate to go around if approach or touchdown is not optimal. 6. Be aware of the limitations and delays in runway condition reporting. Treat all friction data with caution. 7. Experience and simulator practice in contaminated runway operations are rare, so strong airmanship and decision-making are vital. Dear viewers, if you found this video useful, consider liking, sharing, and subscribing for more aviation insights. Until next time, fly safe, and remember, on slippery runways, every move counts. Thanks for watching.